Hello and welcome to this advanced course into the working principles of the waveform editor of the WaverAD signal generator. My name is Kai and I am the CEO of KE-System who are making the WaverAD. If you haven't done the basis video tutorial into WaverAD yet, you might want to do so first, as this course will build on some lessons from this base course. Well, now let's get started into this course. As you can see, I have already started the WaverAD PC software interface. No signal is loaded, as I would like to show you today how to build a new waveform from scratch. To do so, I start the Waveform Editor, which can be found in the context menu of the signal display. Before we start, let me quickly walk you through the different sections of the Waveform Editor. Up here is the selection to select which signal of the current page shall be modified. The current page is the signal display here, consisting of two signals, interface 0 and interface 1. Choices of this signal selection are either one of the two full channels or even single bit lines within the two signals. Down here, one can select the time range within the selected signal that shall be modified. This time range is limited by the two modification cursors, which are the green and dashed lines here in the signal display on the left and right side. This section here then is the main area where the new waveform is defined. This can happen either by mathematical terms from scratch, or an existing signal can be loaded and injected into the current one, into the current signal, which would then be this one here in the signal display. Down here, the user can define how the waveform that has been built or loaded up here shall be modulated together with the signal already existing in the signal display. On the right side is a quick help window which gives indications about what can be done in each individual section on the left side. Down here are two buttons. The try button will produce the result from the calculations on the left and show how the signal would look like in the signal display over here. The implement button will then finalize the calculation and in the end produce the waveform. Let's get started into one real signal generation. This will then show you how the single sections of the signal of the waveform editor work. Okay, let's choose to modify interface 0. Select it here. This is the upper signal in the signal display, which is currently chosen to be an analog signal. Let's work a bit with the modification cursors. Those two fields accept a variety of different inputs. For example, the position of a modification cursor can be defined by time inputs like 1 millisecond. Typing this in, you can see the modification cursor here being placed on 1 millisecond. Other options would be, for example, things like 500 microseconds and so on. Inputs can also be single data points within the signal. Each signal consists of 8192 single data points, and so we can position the modification cursors on those as well, like for example data point 1723, which would be the data point position that is now this modification cursor on. Equally, there are some constants defined that can be used. These constants here in the quick help, one can see them. T, for example, means the end time of the signal or the maximum time in the signal display. The right cursor, for example, that one here, is already placed on T as defined in this field. CL and CR are the positions of the left and the right red measurement cursors. we can use those measurement cursors to position our modification cursors. For example, like this. Typing in CL will put the modification cursor right on top on the position of the left measurement cursor. Those two fields can also work with mathematical terms, combining each of the input options just explained. For example, if we want the modification cursor to be placed directly into the middle between the two measurement cursors, we could use CL as the left cursor plus C, which is the full range between the two cursors, and then half of it. That puts this modification cursor right into the middle between the two measurement cursors. If we want the modification cursor to be 500 microseconds to the right from this position, this would be just adding 500 microseconds to this position. For now, let's leave it with the modification cursors being right on the measurement cursors, so I use CL and CR as our modification cursor positions. Okay, the next topic is the modifications term section right here. As said, this section defines the waveform that shall be used within the modification range, as defined by the modification cursors. Now the table here splits into two columns. One of those columns is the duration. Here we can split the modification range, that one here, into single subranges defined by specific time durations. We can define those durations in different ways. For example, by time values like 500 microseconds, or by a number of data points like 400 data points, or using some defined constants like, for example, those here, the x, which is the time duration within the modification range, so this time duration here. We can also use mathematical terms, combining all of those input options like this. Now this term here means a third of the full range plus another 100 microseconds. The dash, which I use here, is the identifier for the remaining time in the modification range, the time that has not been used up by the above duration definitions. Okay, now we have split the full modification range into 4 different subranges. One is 500 microseconds long, the other is 400 data points long. The third subsection takes a third of the full range plus 100 microseconds, and the fourth subrange takes the time that's left. Now let's fill those subranges with voltage levels. We can use absolute voltage levels, like 1 volt. Of course, also negative voltage levels are possible, minus 2 volts. We can use constants, like this constant Y here, which means the full scale voltage, the maximum voltage that the WaverAD hardware can generate. Also, we can build mathematical terms out of the above. For example, this term, which is half of the full range voltage plus another half volt. Now, to see what we just created, let's watch it in the signal display using the try button. Okay, what we have here are the 4 subranges: 500 microseconds at 1 volt, 400 data points at -2 volts. This defined time range at the full voltage level, and the remaining time at the defined voltage level of half the full level plus half a volt. I think that was quite easy. As you can see, however, in the quick help, the modification term offers much more than just entering absolute voltage levels. Let's go a bit deeper into this. To do so, I reduced the number of sub-ranges to just 2, like this. So what we have here now is we have this full modification range divided into 2 sub-ranges. One takes a quarter of it, the second sub-range takes the remaining 3/4 of it. In the modification term section, we can use several time constants and variables to define the waveforms. One of those constants is the constant t, which is the maximum time over the full signal. We know this constant already from the modifications cursors and the duration input. Similar to the t constant, we have a time variable, which is the lowercase t, which starts with a value 0 at the very left display limit, so right here. With those we can, for example, build a sine wave very easily. Let's choose an amplitude of 4 volts. So the term would then be like this. Let's see what the output is. Now, what we have here is a sine wave with a period over the full signal range from left to right, out of which, however, only the part is used that is within the defined sub-range, which is the 3/4 of the modification range. The full sine wave would look like this. So, period over the full signal range and starting point at the left display limit. Another time constant that we can use is the capital X. This constant defines the time range between the modification cursors. So this time range here. So let's use this in our sine wave and see what the result is. What we have now is a sine wave with a period equal to the modification range, but as we still use the lowercase t variable, this sine wave still starts at the left display limit right here. So the sine wave would look like this. Starting here. Again, only the part of the waveform within the defined sub-range is used. If we want this sine wave to start at the left limit of our modification range, so right here, we can make use of another time variable, which is the lowercase x. Let's use this in our term and see what the result is. Here we are. Now we have a sine wave with a period equal to the modification range and starting at the left side of this range. A third time constant is the capital R. This constant defines the time range within the sub-range in which this constant is used. So as we use it in this sub-range, being 3/4 of the full range, the constant will be applied to this range. Let's use it in our sine wave. Here we are. This sine wave now has the period of the subrange, but still starting at the left limit of the full modification range. So here, as we still use the variable x, so the sine wave would be completed like this, as we only use the part in the defined subrange. If we want the sine wave to start at our subrange, so right here, we can use a third time variable, which is the lowercase r here. Let's use this. And here we are, a sine wave fitting exactly into our subrange. Okay, let's look into another waveform design aspect. For this, I choose the full signal range to be modified. And let's start with a square waveform. This time duration is 1/10 of the full signal range at 4 volt, and another 1/10 of the full signal range at -2 volt. Here's our signal, 4 volt and -2 volt. Now, to have this wave continued over the full signal range, we could of course repeat entering these two lines another 4 times. An easier way, however, is the use of the repeat operator. This is the one down here in Quick Help. Using this operator in a row of the modification table, we'll repeat the signal from the beginning until the subrange is completely filled. Like this. Now our predefined 2 levels are repeated over the full signal range. But now this is not all. The repeat operator can also be nested. Let's try this. We reduce the period of the square wave a bit, from 1/10 of the full range to 50 microseconds. Here is the signal, and now instead of repeating this signal over the remaining time, the full range, we repeat it just for a part of the signal. 300 microseconds. Here it is. Then we add a single sine period to this combination of square waves for another 300 microseconds. Here's our signal, starting with a section of square wave, continued with a single sine wave. Now we want to repeat this whole construction over another period of time. Hence we use the repeat operator again for 1400 microseconds, the repeat operator. Here is the signal, our constructed signal repeated several times by using the repeat operator. The remaining time of the signal, let's fill this with a kind of complex function just for fun. Now here it is. Now this is quite a complex waveform for just 6 lines of definition in the table, isn't it? Let's go into some practical visualization. So far the signal is still a try. If we want to have it output by the WaverAD hardware, we need to implement it, pushing this button. Now the signal is stored and the measurement cursors can be used on it. To output it, we just need to upload it to the WaverAD device, like we do with any other signal. To visualize the signal, I have a PC scope connected to the analog output of the WaverAD device, which is here. The signal in WaverAD can now be treated like any other signal, meaning we can run it in different run modes. In this case I use the continuous mode and push run, and immediately we see on the scope the signal being generated by the WaverAD. Here's our signal. As with all signals in WaverAD, we can of course change the signal in amplitude, in frequency, and of course in offset. This is just as we are used to with any other signal in WaverAD. Now what about adding some noise to our signal? This can be done very easily, and I use this example to explain the remaining options in the Waveform Editor. There is a 1 volt peak-to-peak noise signal in the software package of WaverAD that we can use. Let's load it on the Load tab of the Signal Editor. Here it is. The noise signal is a signal channel signal, so the selection list contains just this one signal that can be chosen. Let's see what this noise looks like. We want the noise over the full signal range, so the modification cursors are placed correctly from the beginning to the end of the full signal range. Pushing the try button does not replace the actual signal, so the green signal on the page, but rather shows what would be the resulting signal if we would implement it like this. Still, the noise is not modulated onto the original signal. This is not what we want. To get the noise on the signal, we use the modulation field. This field offers two special constants, which is Sx and Sm, as can be seen here in the quick help. Sx represents the signal that is currently active in the signal display. So in this case, our quite complex waveform shown here in green. Sm represents the signal that we have created in the above modification area here. So in this case, it's the noise. Now, using those two constants, we can define a mathematical term to bring those two signals together. As we want to have the noise added on top of the base signal, let's use a term like this. Sx is the original signal, the green signal. We want to add the noise, and Sm is the noise. Now, as 1 volt of noise is maybe a bit much, let's reduce the noise level to half a volt. This can be done like this. Let's see how this looks like. Our noisy signal. To output this signal through the hardware, we again need to implement it, upload it, and run it. Here it is, a noisy, complex signal generated by WaverAD. With that, we are through with this course. I hope you enjoyed it. You are now able to use the Waveform Editor of WaverAD to generate your own waveforms or modify existing ones according to your needs. If you are interested in more, check out the other tutorials or the user guide, all on the KE-System website. Thank you for watching this tutorial and keep waving.